Okay, so the orbit stabilizer theorem. We have a group, an S set on which G acts. And the orbit stabilizer theorem states that, there is a bijection between the cosets of the stabilizer of an element S in S and the orbit of S. So if S is in S, in particular, if G is finite, then the size of an orbit must divide the size of G. Okay? Now a consequence of this is Cauchy's theorem, a very beautiful theorem. Cauchy's theorem. What does it state? Let G be a finite group and P a prime dividing the cardinality of G, and G as an element of order P. So double check this is good. Okay, now to prove Cauchy's theorem, we had to resort to group actions, and which is a nice group action. Also, we have seen that the set S is a disjoint union of orbits, right? The two orbits are either equal or disjoint, and the set S can be partitioned into a disjoint union of orbits. Okay? Great. Now, let's prove that. Let sigma be the P cycle 1, 2, 3 in SP, and H the subgroup generated by sigma. Let S be the set of P tuples, a vector of P coordinates lying in G to the P, the Cartesian product of G with itself, P times G times G times G, each component is in G, such that x1, x2, xp is equal to Eg. So you're considering the vectors of P tuples such as the product of x1, x2 up to xp is the identity. Now we've shown, like on Friday, that the cardinality of S is just the cardinality of G to the P minus 1. One reason for that is, technically you can choose G elements for this, G elements for this, and for x to the P minus 1 you have G elements. Now once you choose all of these, xp is uniquely determined, because xp would just be x1, x2, x to the P minus 1 inverse. So you really have the cardinality of G to the P minus 1 element. Now, we have to find an action of H on S. H acts on S. The following way. Let tau be an H, and x1, xp be an S. Define tau star S. Define tau star x1 up to xp to be just x tau 1, x tau 2 up to x tau. Basically, this is just the action of tau on 1, 2, 3p. Okay? Now, first we will show that this action is compatible with the group multiplication. It's not a very that this action is compatible with the group multiplication, with the group operation in SP, or in H, sorry. You see, this action, I mean, let me give an example. What does it do? For example, for P is equal to 3, 1, 2, 3, star, x1, x2, x3. This permutation sends 1 to 2. So I mean, you're just adding 1 technically. So this is just x2. Sends 2 to 3, x3. And this is just x1. Okay, this is what it's doing. Now, need to show, so let tau and sigma be in A, or not sigma, let tau and lambda, let's say, be in H. I need to show that tau, lambda, star, x1 up to xp is equal to tau, star, lambda star, x1 up to xp. This is what I need to show. Well, let's prove that. This is not bad, right? This is just the composition of functions, right? Like the functions is that composition is a group action. Okay. Now there is something important that I need to show, but we'll just do that later. And first, of course, I need to show that the identity on SP. What is the identity on SP? This is the or the identity in SP star x1 xp is equal to x1 xp. But this is obvious, right? Because the identity, yes?
Shouldn't that tau belongs to H?
Tau belongs to H. What did I say? Yes, thank you very much. Thank you very much. So I want the identity in SP. Of course, the identity function, it will not change 1, it will not change 2, it will not change 3. So this is obvious, I guess, right? Okay. Now let's prove this. This is not bad. So what is tau star lambda star x1 xp? This is just tau star x lambda 1 x lambda 2 x lambda p. Well, this is just x tau lambda 1 x tau lambda 2. Really what I'm doing is just applying a permutation on 1 up to p, which is just tau lambda star x1 to xp. Now, of course, the identity in SP is just the identity function on 1 to p. It will just be clearly equal to x1 up to xp. Okay. Now, there is one important thing that I did not show. That this product, that x tau 1, x tau 2 up to x tau p, will belong in S. I'll have the product of the coordinates from 1 up to p belonging equal to the identity, basically. So this is an important fact. We still need to show that, well, sorry, tau star x1 xp belongs to S, namely that x tau 1, that the product of x tau 1 of the x tau 2 x tau p is equal to the identity in G for all tau in H. Now, let's have a look at this. I mean, good thing we have the example here. Now let me get back to this example. Suppose that x1, x2, x3 is the identity. Can you say that x2, x3 times x1 is the identity? If x1, x2, x3 is the identity, can you say that x2 times x3 times x1 is the identity? Can you do that?
No.
Let's have a look. So let me write that x2, x3 as x1 inverse. Agree? If x1, x2, x3 is the identity, then x2, x3 is x1 inverse. So far so good. Let me multiply on the right by x1. Both sides. What do I get? I get x2, x3, x1 is x1 inverse times x1, which is x1. Oh, which is EG, sorry, thank you. This is the key part. This is called a cyclic permutation. You're just cycling them. You know, you're just shifting everything and it's going back. It's not any order that works.
It's every order.
Not every order. Because if x1, x2, x3 is identity, can you say anything about x2, x1 times x3? Not really. You just can say something about cyclic permutations, right? So let's say, can you conclude from this that x1, x3, x2 is the identity?
No.
No. So the choice of h, the choice of sigma here, that is the cycle, is very important. Let's show this. I mean, rigorously, I think it's clear. But if x1, xp belongs to S, then sigma is the cycle 1, 2, 3 up to p, x1, xp, which is equal to x2, x3, xp, x1 belongs to S, since x1, x2 up to xp is equal to the identity, implies that x2, x3 up to xp is equal to x1 inverse, and then you multiply by x1 on the right, and hence inductively sigma to the k star x1 up to xp belongs to S for all k. I mean, sigma has order p, so just k 0, 1 to p 1. Hence S, hence H, and star defines the group action on S. Okay, now I have that H defines a group action on the set S. What do I have? How do I show that the element, that G has an element of order P? Well, we have shown on Friday that belonging to the same orbit defines an equivalence relation on S. And hence the set S is a disjoint union of orbits. We know that S is a disjoint union of orbits, of H orbits. I mean the orbits of the action on H. We call these of H orbits basically. Hence I can write S as union of orb of SI, where let's say the union, let's say from one. Did I ever use n in this? Did I use n in this proof? I didn't. Did I use n? No, I don't think so. Where S1, S2, Sn are representatives of the distinct orbits. Okay, now you remember in your assignment 4, what did you do? You did something. You split the orbits into orbits of size 1 and orbits of size larger than 1. Why don't we do the same? Yeah.
From assignment 6, does that mean that this is
Assignment
a
four.
normal set? No, 6. The recent.
Pardon me?
Does this mean this is a normal set?
Where? What is a normal subgroup?
Because it's a union
Ah!
classes.
So you're saying a normal subgroup is a union of equivalence classes? No, I don't think. I mean, you could use this, but you could do it for more principle. I mean, but let's not talk about the homework. Okay? Great. So S is disjoint union of the orbits. Now, let's do this. So let's say let S1 up to let's say Sk be representatives of the singleton orbits and Sk plus 1 up to Sn be representatives of non-singleton orbit. Of course, I know I have an orbit that is a singleton. If you take the vector of the identity, this is invariant, right? Identity, 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 identity p times. Apply any permutation, it's invariant. Agree? And the product of these, the product of the identity p times is also the identity. Okay? So really I know that I have a singleton orbit here. Note that in GP let's see, in GP is fixed, satisfies the orbit of EG is equal to ET, is equal to itself. Okay. So what I have here, I can split S into a union from I equal 1 to K orbits I also this joint union here, the union from I equal k plus 1 to n or Si. These are the singleton orbits, and these are the non-singleton orbits. Now the singleton orbits, what's the size of a singleton orbit? 1. So this has k elements. Very good. Now, what is the size of this? So an orbit divides the size of the group. So it's either 1 or p. Now I'm telling you it's not a singleton. So the size of this, what is that? P. So this one here, this union, I can just say it's k times p. It's a multiple of p. Agreed?
But
If each of these one is p, then not k, but q times p. Agreed? So k plus q times p. Okay. Now what is S? S is g to the p minus 1 is equal to k plus qp. G to the p minus 1 is the, yes sir?
Just q is n minus.
N minus k, exactly. Okay. Now p divides this side because p divides the number of elements of G. And p divides this side. So p will divide. So p divides k. So p divides the number of singleton orbits. Agree or not?
Yeah.
This is the same argument that we have done before. Yeah or no? You remember this argument? P divides the size of G modulo Cxi. P divides G, hence P will divide the size of the center. And the center is, the size of the center is the number of the singleton orbits under conjugation. Same argument. Now, how many singleton orbits do I have? What can I say about K? The number of singleton orbits. At least, how many do I have?
At least one.
At least one.
Yeah.
K is at least 1. Now that P divides K and K is at least 1, what can I say about K?
K is a multiple of p.
K is at least P. And since K is bigger or equal than 1, then K is bigger or equal to P. Okay, great. Now I claim that this is kind of done. We're almost done here. This is a kind of argument that is a boom, very beautiful argument. When is an orbit singleton orbit? Now let's say x1, xp be in S such that the orbit of x1 xp is itself. This happens if and only if tau star x1 xp is equal to x1 up to xp for all tau in H. Of course, we also have the condition that x1, x2, xp is the identity. Now, I'll let you convince yourself that since H is cyclic, it's enough that sigma, the generator, fixes x1 up to xp. If and only if sigma x1 xp is equal to x1 xp and x1 x2 xp is the identity since H is generated by sigma. Okay, try to convince yourself of this fact that if the generator fixes the group, then the entire subgroup generated by the generator, which is the whole group, fixes the element. Okay? Now, what is sigma applied to x1 up to xp? If and only if x2, x3, xp is equal to x1, x2, oh sorry, x1, xp, oops, xp, and x1, x2, sorry, oh man, I already, and x1, x2 is equal to the identity. Well, this happens if and only if what? Look at the first component. This tells me that x1 is equal to x2, right? The first component tells you that x1 is equal to x2. The second component tells you that x2 is equal to x3. So all of these should be equal. And is equal to EG. Right? Now let's just replace. If and only if, well, wait, it should be clear as an if and only if. That if and only if x1 to the p is EG and x1 right? Well, if x1 to the p is EG, what can I say about the order of x1? It must divide p, right? If x1 to the p is EG, then x1, the order of x1 must divide p. Now I know that there are at least k of these, that there are at least p of these. So I can find an x1 that is not the identity that satisfies this. Because I know there are at least p such fixed points, there are at least p such possible singleton orbits. There are at least p singleton orbits. Oops. Hence any singleton orbit. Hence singleton orbits are of the form x, 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 where x to the p is the identity. Since there are, the number k of singleton orbit is bigger than p, there exists x that is different from the identity such that x to the p is EG. We have shown that there are at least k possible singleton, p possible singleton orbits. I know that the identity is one of them. And I know that all singleton orbits have this form. So you can pick one, you can pick an x that satisfies x to the p is equal to EG, and x is different than the identity. What is the order of x in this case? The order of x divides p, but x is different than the identity. Order of x. Order of x divides p, and p prime. And x is different than 1, so x has order. Ta-da! The proof of that, I think, appeared in a paper by Mackay. The paper was like 1 page, no, half a page. He says define this, and then conclude this. It's the same proof. I don't think that's the original argument due to Cauchy. I think the argument due to Cauchy involves the class equation. But yeah, this is a very nice proof. Okay. Great. Are we good here? It's a bit not easy, it's not easy, but try to digest it. Try to see how this works. So this argument we'll see again. Yes?
Can you explain the intuitions to why you need to do this proof via group actions?
I mean, there's another proof via another group action.
Yeah, but how do you when you look at the
how do you know? How do you know? I mean, this is why it's a published paper, because it's a new idea, right?
Okay, so
yeah,
because the fact that you use group action is a bit
sure. I see your point. Whenever you have a group of size p to the k, okay, say the group is some prime to the power k. Remove all, you have a disjoint union of orbits, okay? Now the singleton orbits, leave them aside, and you have the non-singleton orbits. The non-singleton orbits have size divisible by p. That doesn't work if p is not prime. That doesn't work if the group is not of size p to the k. So this is one way to motivate this. Okay, we will see this. Okay, but that's a very good question. Whenever you have these groups that we call p groups, groups of power p to the k, it's not a bad idea to think of group actions. Just because of the nice counting arguments, nice divisibility arguments that this provides. Okay, great. Yes.
Since there's always some x that has order p, that means that there's always an element that has any order that divides g?
No. Any order of prime dividing g.
Yeah, but if you make an element by multiplying two elements that have different
S3 doesn't
prime.
have an element of order 6.
Yeah. Wait, why again?
S3, look at the order of the elements. It's 1, 2, or 3. And S3 is not cyclic. U8 doesn't have an element of order 4. Z2 cross Z2 doesn't have an element of order 4. It really works for prime numbers. Okay? Great. Now let's move on to some more theory on group actions. Again, so I don't expect you to be fully focused with me, but I have to continue. But I hope that on Friday you guys are, catch your breath again. After you do well in the exam, in the midterm, you catch your breath, and then, we can do some more theory on Friday. I mean, I have yet to decide if I'll do a new thing on group action or just continue with applications of this. But please try to review your notes on Wednesday night, after your whatever exam you have on Wednesday night. Okay? Yes?
I'm not sure to understand the notation of doing x2, x3, x4. Is that symmetric?
That's a p vector. That's a vector where every coordinate lies in G. Just you say Rn, every number lies in R, right? Here every x lies in G. Every element lies in G. The Cartesian product of G. These are elements of G. Okay?
Okay.
Yeah? Every x lies in G. So this is a vector in the Cartesian product. Okay, great. Now, the relation between, why do we study group actions? Why are group actions fit well in this course? That's a good question. And then we will see. Theorem. A G-Bay group and S a G set. Basically, a set on which G acts. There exists, so G acts on S, say, what? Then, there exists a homomorphism of groups, of course, from G to the symmetric group of S. So if I have a group action on a set S, then I can find the homomorphism from G to the symmetric group on S. Let's prove that. This is like the proof of Cayley's theorem, by the way. The proof will follow the same steps, except I will not be able to show that it's injective. Okay, proof. So we know that G acts on S. It sends GS to G star S. Define. So first of all, let lambda, so fix J and J, well, fix J and J, or let J be J, and define lambda J from S to S to be the function that sends an element little s to G star S. Run out of chalk soon. Claim lambda of J belongs to the symmetric group on S. Basically, lambda of J is a bijection on S. That's what, yes sir?
What does G set mean again?
It's a set on which G acts. So you have an action of G on S.
Okay.
Okay? G set. The set is a G set. Okay? I defined this before, right? Did I say G set? Yeah. Okay. So lambda G belongs to the symmetric group on S. Let's prove this. You remember Cayley's theorem? If S is equal to G and the star is just multiplication, this is a bijection, right? Let's prove this here. Now, I'll just do it by finding an inverse. What's a good candidate for an inverse? I would say that lambda J, circle lambda J inverse, is the identity on S. Since lambda J, compose lambda J inverse applied to S, what is that equal to? This is just J lambda G star G inverse star S. This is just G inverse star S. What is G inverse? The identity. What's the identity star S? S. Okay? Do I need to write this down or it's clear? It's clear, right? Identity star S is S. Similarly, I mean, you know, by flipping G and G inverse, if you will, but let's do it again. Similarly, lambda G inverse is the identity on S. Okay? The same proof works, right? G inverse G star S, this is S. Hence, lambda G belongs to the symmetric group on S. Now define a map, define rho from G to the symmetric group on S that sends little g to lambda G. I claim that rho is a homomorphism. Again, it's the same proof as Cayley's theorem. Look at the proof of Cayley's theorem and look at this proof. They're almost the same thing.
What is the difference?
Well, the Cayley's theorem, S is equal to G, and the star is multiplication, G, H, right? This is not, S is not necessarily a group. Okay, so rho is a homomorphism. Again, by the way, the final exam will contain a lot of group actions. Okay, so please be comfortable with that. Okay? The final exam will contain a lot of group actions. Okay? At least that's what I find. So please be comfortable with that. Okay? So what does it say? What do I need to show? And I'm trying to do the least important stuff now, so that I do the practice problems on Friday Monday and Wednesday. Okay, so that you're at least focused on this stuff. Now, I need to show that row G1, G2 is equal row of G1, let's say composed with row of G2. Now, what I need to show really is that lambda G1, G2, lambda G1 composed with lambda G2 is equal to lambda G1, G2. Well, this is more or less obvious. What is that? Lambda G1 composed with lambda G2. So let S be an S. Same proof as Kelly's theorem. Almost the same proof. So this is lambda G1 applied to lambda G2 of S, which is just G1 star G2 star of S. Now what is this equal to? By properties of the group action, this is equal to, what is that equal to? G1 star G2 star of S?
G1, G2 star S.
G1, G2, very good. Which is equal to lambda G1, G2.
Of S.
Oh, yes, thank you. Yes. Hence, lambda G1 circle lambda G2 is equal to lambda G1, G2. Hence, rho is a homomorphism. Agree? Hence, rho of G1, G2 is equal to lambda G1, G2, which is equal to lambda G1 circle composed with lambda G2, which is just rho of G1 composed with rho of G2. Now it becomes a race. Do I finish first or I run out of shot first? Let's see. Okay.
I mean, you could use your fingers for a little moment and there will be some erasing.
Yeah. Okay. Now, so I have a homomorphism from rho to the symmetric group on S. You guys should be excited when you see this. Like, this is a very, very important theorem.
I don't understand what you're wanting us to learn.
That a group action is a homomorphism from G to the symmetric group. That's it. If you have a group action on S, say you have a group action of G on 3 elements, then you have a homomorphism from G to S3. Now, homomorphism from G to S3, what can you do with homomorphisms? You can study the kernel. You can apply the first isomorphism theorem. You can do all of this stuff. So really, a group action is just a homomorphism from G to the symmetric group on, if S is finite, say, with n elements, you have a homomorphism from G on S head. Now, it looks very dry. On Friday, we'll do a lot of applications for that. Again, if you want me, I plan to do some applications today, but I feel like I don't think it's the time to.
I think it's the reverse. We need a lot of psychology.
Yeah, I'll give applications, but
it's really hard to understand the theory you give us when it's hard to kind of think how.
Yeah, I mean, on Friday you will see how. On Friday or on Monday.
Hopefully.
Okay. But if I give you now things, if I give you an application now, it will just be tough to understand why it's happening. So the idea, if I have that G acts on a set with n elements, what do I have? I have a homomorphism from G to Sn. Exactly. Now, if I tell you that G is a simple group, so G has no normal subgroup except the identity and itself. And it acts on a set with n elements. Okay, think about that. What can you say about this action?
Can you repeat?
Yeah.
Sn is non-simple.
I'm not talking about Sn, I'm talking about G. Very good. No, very, very good. So G, you have a homomorphism from G to Sn. And G is simple. So what can you say about homomorphism? What can you say about the kernel? It's either the identity, right? Or it's equal to G. Right? Now if the kernel is equal to G, this means that G will fix every single point. in the group action. That G will not act. Basically, G will act like if it were the identity. Okay? G will fix every element in S. Think about that. And if the kernel is the identity, this means that G injects into Sn. Pretty cool, huh?
What
Pretty
does
cool.
fixing mean again?
G, if the kernel is the identity, this means that G injects into Sn. Then you have a injective homomorphism from G to Sn. Yeah, very good. That's look, this is what you should think about this. This is not obvious stuff. Now let's look at the kernel of rho. The kernel of rho is the set G and G such that lambda G is the identity function in S. What is that? I mean, if you have time, we can do, well, we'll do an application on Friday. Now, what is this? So G belongs to the kernel of rho. If and only if lambda G is the identity function on S, which means if and only if G star S is equal to S for all S in S. If and only if G belongs to stab S for all S in S. If and only if intersection, well, and only if G belongs to the intersection of all the stabilizers. So the kernel of rho is equal to the intersection of all the stabilizers. Okay, I'll give you a small example using group actions. Maybe I have 2 minutes left, so maybe I just should talk a bit. Okay, I'll give you a small example. I mean, if I just take 2 more minutes, I'll just give you an example. You have seen in an assignment that if n is normal subgroup of index n, then G to the n will belong to n. You remember this for any G in G. And you have also provided a counterexample where if n is not normal, this won't work. Right? You remember this? It's in your exercise 1 for which I posed the solution, and which you should study, by the way. But yeah, okay? Now you can prove something else using group action. That if H is a subgroup of index n, not necessarily normal, then G to the n factorial belongs to H.
What?
Yeah. The idea here is that you have to consider an action. So I'll do this more on Friday. So G is a group, and H is a subgroup of index n. Okay? Now you can find an action of G on G mod H. You send G and a coset XH to GXH. Suppose that H has index n. Now this action, you don't have to write this, but I'll rewrite this on Friday or Monday. Now this action will give you a homomorphism from G to Sn, whose kernel is contained in H. Because if you let G be in H, if you let, well, we'll see that, okay? Anyways, if you let H here, and you consider this H, you get back H, okay? So the kernel is contained in H. So H contains, the normal sum contains n normal in G, with G index n is equal to n factorial. Well, less dividing n factorial by the first isomorphism theorem. Now apply this result that you have done to this group, and you see that. Okay, this is a bit fast, but we'll see this on Friday. Okay.
I don't understand anything that happened in this class today.